Okay. All right, so I'm going to share my screen again. And that looks like it's there. So these slides are actually some fraction of them from a colloquium I gave last week at the Argonne National Lab, talking about experiments that they're heavily involved in and our interpretation of them. So I hope you will interrupt frequently and ask questions. I don't have a particular agenda. I have an outline of things I'm trying to get to, but I'm happy to go off on tangents according to what's interesting. Okay, so the idea here is changing the picture of the atomic nucleus. So let me just go to my next slide even. Actually, I just mentioned here, by the way, so I have funding both from the National Science Foundation and the Department of Energy for doing the kind of work I do. I'm part of a collaboration of about 50 physicists and computer scientists and applied mathematicians, statisticians, called Nuclei. That's the Nuclear Computational Low Energy Initiative. So some of the things I'll mention about the computational side are connected with these big efforts here. Okay, so what I wanted to tell you about is how we have these different pictures of how the nucleus looks, and we use that to guide our intuition about what kind of experiments we want to do and how to interpret it. So I'm going to give a little bit of very brief history, just a couple of stops on the way to what the modern picture is of things. And the idea is there's kind of a conflict in pictures, that there are experiments that seem to imply one picture and features of the nucleus that aren't there for the nuclear structure that I do. And this has been rather a controversial thing over time, and people insisting that we're missing things and so on. But we actually do understand this, and the key buzzwords here are renormalization group. So I hope to give you an idea of what the renormalization group is and how it fits in. It's got a very big Ohio State connection. The methods that I'm using were invented by Ken Wilson and collaborators here, including Robert Perry, who some of you might have had for quantum. Invented here like 20 years after he did work on the renormalization group, for which he won a Nobel Prize. Okay. So let's see how this goes. Okay, so I want to go way back to the beginning of nuclei, before there were nuclei. So J.J. Thomson had this model, so a picture of what a nucleus is, and this is the entire atom, and the positive charge is spread out through the whole thing. Okay. So this was consistent with the data they had, which was atoms were neutral, and that's about it. Okay. But then Rutherford came along and did an experiment I'm sure you're all familiar with. Alpha particles. This was high energy at this time. So high energy then meant 5 million electron volts. And the result was that sometimes the alpha particles came backwards. And a famous quote, he said, it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So now the nucleus was just a tiny thing inside the atom, and hence it was a nucleus. This model explained the observations of the angular distribution of the alpha particles that they saw. Okay. So this is sort of the first case of having pictures giving you intuition here, and an experiment telling you that one of these pictures was simply wrong, because in this picture nothing got deflected very much. So let's jump ahead 50 years. Okay. So now a lot of information has been learned about the nucleus. And in particular, one had information about the energy as a function of how many neutrons and protons. And there were certain blips in it that happened at various places. And this was also associated with the abundance of different elements that were noted. And it was noted that it looked parallel to the very successful description of atoms, which had this shell structure where the atoms, the electrons basically moved independently of each other in some mean potential that came from the nucleus and the other electrons. And so they looked for a parallel. This was tricky, and it was worth a Nobel Prize to Gerhard Meyer and Jensen to figure out how this actually worked. So they came up with what was called the nuclear shell model. This was a picture from Gerhard Meyer's Nobel Prize talk about magnetic moments. And the sort of takeaway from this picture is that some things were predicted by the model, the magnetic moments, and worked quite well, but it wasn't super precise. So it wouldn't be surprising if it was not perfect. What was the picture in this model? So the picture in here is just that the nucleons were moving in something like a square well due to all the other nucleons. And they were just all independent levels. And those levels were filled up and made these shells. And there were certain stable places, which were magic numbers. And the tricky part of nuclei is that there was an interaction between the spin and the orbital angular momentum, the spin-orbit coupling, that was much, much stronger than in electrons, and that changed what the magic numbers were. So all of this was good, seemed to explain things, not at high detail. So there was a problem. There was existing data that consisted of neutrons and protons scattering off each other. And it had this kind of behavior here. I don't know if any of you have done scattering and learned about phase shifts, but it's just it's a property of the wave functions that is related to the cross section. And the bottom line here is that the fact that it's positive for low energy and change sign for high energy meant that the interaction between these two nucleons, so they're not in a nucleus, they're just in free space in a scattering experiment, is attractive if they're a long way apart, but if they got close, it became repulsive, and that made this go negative. So the cartoon then of the potential between these two looks something like this, with this attraction and then this very strong repulsion. This is broken because this just goes way off the page. Okay. So the Coulomb interaction would look something like this, but would just keep going attractive here. The fact that this had this repulsive core meant that it seemed very strange that the net effect, if you're inside of a nucleus, was that the different neutrons and protons acted independently, because when they got near each other, they should really see this. So there should be what we would call, and what they call correlations, things beyond this. So Keith Bruckner and collaborators in 1955 wrote a paper, and this is the first part of it, said that at the time, the fact that the shell model was successful had people thinking that this picture somehow went away when you went inside the nucleus, that there was some sort of nonlinear effects that got rid of this core, and you could represent this by this uniform field that's represented by this kind of square well that we have here. That paper, though, was basically, that was the introduction to say that this assumption is completely wrong, because they had a number of experiments, and this time now called high energy as well. Before it was 5 million electron volts, now it's 100 million electron volts. And what they found is that these experiments could only be explained if the momentum distribution was different than what the shell model would predict. So my whole discussion is about momentum distribution. So let me say a little bit more about that. That just means the probability to find protons and neutrons with different momenta. Okay, so moving really fast in there or moving slow, and that's a property of the wave function. So why did they think that? So let's make a little picture here. The question mark here is to say, what is the picture of the nucleus now? The experiment is called Deuteron Pickup, one of the experiments. And the idea was they shot in neutrons at high energy, fast ones. And a lot of the time, deuterons came out. So a deuteron is a bound state of neutron and proton, and it's only just barely bound. It's bound by 2 MeV as opposed to this 100 MeV. So this is a very unlikely thing to happen if your picture of the nucleus is one associated with the shell model, where the key thing here, don't worry about these going in random directions here. The idea is none of them is going very fast. And if I tried to calculate the likelihood that this neutron would pair up with a proton to make a deuteron, it's just very, very unlikely. So if you did in quantum mechanics a calculation, for example, with Fermi's golden rule, you would find that this is just very unlikely. The matrix element is too small. So what Bruckner and al. Said is there had to be in the wave function a probability that there's a proton going really fast. So having high momentum like we have here. Let me just switch to a laser pointer. There we go. Like this. And furthermore, he said, whenever you found one like that, you're going to find another nucleon, proton or neutron, going roughly the opposite direction. So the center of mass of these is small, but the relative momentum is very large. And where did those come from? Back to this little picture, they came because of this repulsive core, that when these nucleons in here interact, there's a good chance because of the core that they will be kicked up into intermediate quantum states that have very high momentum. So the wave function would have that very high momentum. So they did their basic calculation, which might actually be like a homework problem these days. And they calculated what distribution of momentum, probability of momentum you need to explain the data. And what they got is something like this. This is as a function of the energy of the particles, that they had this big tail. This is a semi-log plot here. So the probability is low compared to these low momentum, but it's still there. And this is what you would have said from this shell model picture. Okay. So it's a very different picture of the nucleus in that case. What was their conclusion was that it means that the assumptions of that shell model, that they move independently, can't be correct, and it has to be only an approximation. And a consequence, if you really want to explain the nucleus, you're going to have to take into account these high momentum pieces and the fact that the potential looks like this. There was a sort of fly in the ointment here in doing this. Oh, and by the way, this feature of the wave function is what is called a short range correlation, or SRC. So people, if you read Nature or Science every year or so, there's another paper talking about short range correlations in nuclei, and this is what they're talking about. So there was a little hitch in this, is that they didn't take into account in their naive calculation that when the neutron comes in and the neutron and proton are coming out, they're going to interact with all the other ones in here as well. And those are called initial and final state interactions. And what they do is just kind of share the momentum a bit and distort this nice picture. So it really wasn't completely convincing anymore. And that was going to have to take another more than 50 years before they figure out how to do this. Okay. So this is the experimental side of doing this, but it says that the theory, we better learn to deal with this potential. And here it's a story of about 40 years of trying to calculate nuclei with one of these potentials. I'm referring them to hard. Hard refers to having this repulsive core here, which means that they have this very high momentum, which makes it very hard to do calculations. So it's hard in two senses there. What people did is develop very precise potentials. I had that little cartoon picture before of what it looked like, but they developed ones that were extremely accurate in reproducing the data from neutron-proton scattering, but they were very, very hard to calculate with. So you can just imagine if you have this thing, it's like a square well going up to infinity. The wave function has to die there. And that makes it, when there's more than a couple of nucleons, a couple of neutrons and protons, really hard to solve the problem. And basically, people tried that all through the 60s, 70s, and 80s. It wasn't until these folks at Argonne, Steve Piper and Bob Varinga, used Monte Carlo calculations. This is Green's function Monte Carlo, to use this potential and calculate. And this is a famous diagram that they came up with, which is the energies in all of these light nuclei. So these are total, this is 2 protons and 2 neutrons in helium-4, up to 6 protons and 6 neutrons in carbon-12. And the key observation is, here's the theory, is these yellow-red lines. Green is experiment. And given just this input here, they were able to reproduce all of those. So it was really the first time that it was clear that this picture really could generate nuclei, at least up to carbon. So what else could they do? Once they could do that, they could calculate the wave functions very accurately. And this is the momentum distribution of the protons. And what they found is that for smaller momentum, which in this unit means, say, up to 0 to 1 or below 2, there were differences in the nuclei, but all of the tails, which were there, which were predicted by Bruckner, were the same. Okay, so that's a feature that we want to observe from this. These were very hard to calculate. And this was the progress over 40 years of this, or let's take it up to here, to go from the total number of protons and neutrons, just of a few back in here, up to just this point here, using these forces. And these were done with this Monte Carlo. So if one wanted to extrapolate, you can see there's basically a linear extrapolation. To get to calcium-40, which is still not a particularly big nucleus, it's a medium-sized nucleus, it would be another 20 years from now. So this was not so good. What was going on at the same time is people who didn't like these hard potentials used other methods. They developed this shell model further, and they did something called nuclear density functional theory. And those interactions were soft, meaning they had none of this high momentum stuff. And they seemed very successful. So then into the 2000s, then we're set up for a conflict between these two pictures, one that where things were soft and more independent of each other, and ones where they were highly correlated and we had these hard potentials. Which was the right picture? And so that takes us into the modern era of things. So let me just pause and see, nobody has jumped in and asked any questions yet. Any questions at this point? No? Okay, we'll see you on the next section. Okay, so in between there were a lot of experiments. I've skipped a lot of that history, but the real key thing was about 15 years ago when they first started this, and they only perfected this in the last few years, what they did is started doing experiments that actually tried to detect these short-range correlation pairs, these high momentum pairs that were sort of back to back. And the idea was that they developed the experimental capability to do electron scattering, where a virtual photon would knock out, say, the proton from this. And because this one already had a high momentum, it would knock out the proton and this would go flying out the other direction. So the signature that these existed were two fast-moving nucleons coming out. So it's something analogous to what we had before with the experiments with this deuteron, but in this case, very cleanly detecting these things. So just to say that a little bit more, this is a sort of Feynman diagram of what happens. This photon comes in, we have this pair of high momentum nucleons, one of them gets knocked out and this one goes in the other direction. And the fact that you are detecting, you know the momentum of this photon coming in, you know this one coming out, and you measured this one, so you could work backwards and say that these two were actually back to back. Okay. And then it would seem pretty convincing that this is the correct picture of what's going on, this cartoon, where we had some region which had that shell model type picture, but a lot of the nucleons were up here. From their measurements, they said 20% of the nucleons were high momentum. And because higher momentum means higher kinetic energy, a full 70% of the kinetic energy of the nucleus were in these pairs. So this seemed like a very definitive demonstration that this is what a nucleus looks like. And that this picture, where we had these red ones in here 20% of the time, was the right picture. Okay. Finally, an unambiguous measurement. They've been trying to measure the nuclear momentum distribution for almost 50 years, and maybe they finally have it. Okay. So there were interesting features about this that have been published starting in 2008. One of them was that of this 20% of the nucleus, almost all of them were neutrons and protons. Okay, so they did a lot of measurements and found only 4% of the pairs were proton-proton. So this is weird because if you think of something like carbon, it's half protons and half neutrons. So just by counting, you'd expect maybe there's fewer proton-proton pairs because you can count neutrons and protons, but it'd be like 1/3 and 2/3. Okay, not 4%, only 4% of proton-protons. They did other things, and they measured that if they changed how many neutrons there were compared to protons, so carbon has an equal number of neutrons and protons, lead has about 50% more neutrons than protons, that in fact, if you just think about it, you'd expect that the neutrons would go faster because they're fermions and therefore they would pile up more. But in fact, of these high momentum ones, they found that the higher percentage of protons were faster. So this was described in Nature as the journal, protons speeding up. Okay, what else did they find? They found that this is the most recent one, this is not even published yet, that if they cranked up the energy so they could measure as a function of momentum, that they could change this fraction that they observed. So they were observing this place where the fraction of neutrons and protons was like 95%. If they go up to higher energy, then it was more the 2/3, 1/3 that you would have expected. So what they figured out that was actually probing a property of the interaction between neutrons and protons, which is something called the tensor interaction. So it's a different type of interaction than you're used to. This depends on the spins of the nuclei, of the neutron and proton, as well as how far apart they are. So it turns out that affects neutron-proton, but not proton-proton. So if you sit in a region where this dominates over this repulsion, you get this, and then it fades to this. So it seemed like they could describe this whole thing very well. If you take this picture and turn it into a phenomenology, a way to explain this picture, you would say that that the momentum distribution, so how likely it is to get this momentum, was something that only depended on the nucleus times something that only depended on these two nucleons. And it sort of separated this dependence. So I won't go into the details of this. This had some quantitative predictions, and basically they found that it worked. That when you did detailed calculations, you found that all of these wave functions looked the same at short distances, even though they looked very different when you had a pair of neutrons and protons further away. This was universal. And when you looked at ratios of cross sections and made predictions, that you got the same answer for all different potentials. Okay, so there's some specific set of predictions that they made. So this picture, again, just seemed to work just fine. So this isn't good in the meantime, by the way. I was one of the people working with these soft potentials, that they were seemingly doing these experiments showing that the picture that I had was completely wrong. But we didn't believe them. Let me go back to this picture. This was the one I had before with the rate of improvement in the theoretical calculations. It would take 2040 to get to 40. What actually happened was this. Took a sharp left turn, got to 40 5 years ago, and have just kept going. This was in large part to work that was actually done here at Ohio State in our nuclear group. That the key ingredient was to use these potentials that were thrown out in the 1950s, supposedly. So none of that high momentum. This is another picture of what progress has been made. This is by Heiko Herget in a recent review. He was a postdoc here as well. He's faculty at Michigan State now. If you put the number of protons and number of neutrons, you could put a little square for every possible nucleus you could have. So this is actually just a fraction of them. We think there's something like 7,000 that we could discover, and about half of those, or less than half, 3,000 have been measured. But calculated in 2010, we could do just these little guys down here, just those. As of this year, we could do, or last year, we could do all of these, and we're about to fill in all of this stuff here. So this is part of it where this takes some heavy duty computing to do, but it's all still feasible. And many things could be calculated, and it's all based on this kind of simple picture. So how do we reconcile these two pictures? So I'm going to give you the answer and then tell you how this relates to the renormalization group. And so these are cartoons of what are happening in the scattering that I mentioned. So in the hard case, the idea was that the photon came in, it interacted with one of these high momentum pairs, which were in the wave function, and knocked it out, and the other one went flying the other way. But there's another explanation, and that's that the wave function is completely soft. It's just simple things, and that the interaction is not with a single nucleon, but it's with two nucleons at a time. And that's our picture of what happens. This goes with this hard picture, this goes with the soft. So there are two different physics interpretations of the same event. So this is something that you might call the nuclear Roshuman effect. Okay, so this is well before your time. It's well before my time, but I've seen this movie, classic movie by the director Kurosawa, in which there's an incident that happens and a bunch of witnesses, and all the witnesses tell contradictory stories about what happened. So this has gone into the lexicon as the Roshuman effect, contradictory interpretations of the same incident. So we seem to have two contradictory interpretations of the same experiment. And which one is the correct one? So that tells us, it takes us to the key thing here, the renormalization group, which just to give the punchline away here, is going to tell us that both of them, or an infinity, a continuum of descriptions in between, are all good. So I'll just tell you a bit about how the renormalization group works. And again, jump in to ask any questions about this. There's two ideas about the renormalization group to talk about. The first one was related to phase transitions. So you may have taken statistical mechanics and did an Ising model where you had spins up and down on lattice sites. Well, Kadanoff in the 1960s described that what you wanted to do to understand the phase transitions was to get rid of all of these little details at short distances and average over these and replace these spins by a single spin here, so that you get rid of the short distance stuff and leave the long distance remaining. So this is Ken Wilson back in late 60s, early 70s. He won a Nobel Prize for taking this idea and formalizing it and making it work. And explaining things like critical phenomena, second order phase transitions, and universal behavior. So what was that about? So the picture here is all matrices. So think of a Hamiltonian matrix when in momentum representation. So low momenta to high momenta going this way. And what Wilson said to implement this kind of idea is to say, let's make a cutoff in here and set everything to 0 above that cutoff. And then we're going to lower it step by step. But in doing so, we're going to change the Hamiltonian at each little step such that the eigenvalues, the observable quantities at low momentum don't change. So we're going to take this big matrix here and reduce it down to eventually we have a small matrix like this. That step-by-step change in this is done with, is like a differential equation. That's what the renormalization group is. The group structure isn't really very important. That name came from a long time ago when people thought it was important, but it's basically this change of what happens as you integrate out, you remove short distance physics. So high momentum means short wavelengths, you're getting rid of it. So David Gross, who won a Nobel Prize for discovering asymptotic freedom in QCD using the renormalization group, said that the idea is that you have different scales. So scales of high momentum, low momentum, or long distance, short distance. And if you want to go to the larger scale, you can do that just by taking little bits of the smaller scale, okay, and throw away most of the details. So this is the principle of renormalization, that we can do this. So the renormalization is changing that Hamiltonian to take into account these effects, but we can really make it work with getting rid of all of these details. Okay. Another way to look at the renormalization group was done in field theory, in quantum electrodynamics originally, and then quantum chromodynamics. So this involves perturbation theory. So if you've taken quantum mechanics, you may have done perturbation theory. And you do first order perturbation theory is sandwiching a Hamiltonian or an interaction between the ground state. And then you have second order, which is a sum over all the excited states. And perturbation theory fails if that second term is bigger than the first term, right? You want it to be smaller. And in QED or QCD, the second one was supposed to be smaller because the strength of the potential was small. It was perturbative, you'd say. But in doing that calculation, that sum over the intermediate states, you could get large contributions, large logarithms. And what the renormalization group does is enable you to shift contributions from that sum over states back into the lowest order perturbation theory. And it makes something that doesn't converge and makes it converge. Okay. An example of that is what's known as the running coupling in QCD. So this is the fine structure constant of QCD, the strength between quarks and gluons. And if you change the distance scale at which you look at it or the momentum scale, it changes how big it is. And particularly it gets very small if you go to very high energy, and that's called asymptotic freedom. What this means is that your picture of what happens in QCD, and I'm just going to actually go to that picture here, also changes when you do this. So these are what are called parton distributions. It's essentially that momentum distribution I was talking about, but not for a proton and a nucleus. It's for a quark and gluons inside of a proton. And so if you look at one resolution scale, so one, this corresponds back to my picture here. If you look with my lambda down here, you get very different picture than what you get up there. And you go from something that has a lot of strength in this variable up here down to something that doesn't. Okay, so the details of that don't matter for us here. They're different in a nucleus, as I'll see when I'm finishing up this, but they change. Okay, so the picture changes when you run the renormalization group. There's a famous essay by Steve Weinberg about why the renormalization group is a good thing quite some time ago. And what he said is that in both these cases, this application and in the one for phase transition, the idea is to figure out, to arrange so that the degrees of freedom, right, which means the variables that you're using, are the relevant or most efficient ones for the problem at hand. So what the renormalization group lets you do is change the variables that you're using. So what does this have to do with low energy nuclear physics? Well, it turned out that those two ways of doing it, there was a third one that developed that I had mentioned. Ken Wilson did his Nobel Prize work back in the 1970s. But 20 years later, while at Ohio State, this is him later, with Stan Glazik, he and simultaneously Franz Wegener, who also worked on things in the 1970s, independently invented a different type of renormalization group, which was unitary. And Glazik and Wilson actually called their similarity renormalization group. This is a little more general than a unitary transformation. But it's a way to, if we think of this matrix, instead of making the matrix block, just having a small block down there and throwing away all this stuff, you make it diagonal or block diagonal. And go ahead. Oh, okay. Sorry, I see that. Oh, you found the, yeah. So that actually is from a summer school that I was one of the 2 lecturers at some years ago, 2013, I think it was. That's a great thing. You should read things that Steven Weinberg says. He writes a lot of essays over the years, and very smart guy with very interesting things to write about. So why does this work? Well, up here, the idea is, you know, how do I use one of these matrices? It tells me that if 2 nucleons come in with a relative momentum like this, the size of the matrix elements tells me the probability that they'll go out with this other matrix, this other amount. So what this does is it makes it only low momentum talking to low momentum. What this does is it make it low momentum only talks to low momentum, and high momentum is still there, but it only talks to high momentum. So it turns out this is great for nuclear physics, and this is just some of the folks who were developed it while they were young scientists at Ohio State, Scott Bogner and Achim Schwenk, and we developed this. It actually took some time, so it was around 2006 that this started taking effect. And then over the next years, the next, say, 10 years or so, people learned how to put it into their codes, and that's where we had that really rapid increase in the calculations. So let me just sort of finish by telling you what this looks like pictorially, to hopefully give you an idea of why this makes the soft result work. So I'm going to take Weinberg's title and say, why is the similarity renormalization group a good thing for atomic nuclei? So this picture that I showed you of the potential is what you'll see in basically any textbook on nuclear physics. That's what it looks like with this repulsive core. If you Fourier transform that and make it into a matrix, so here's the Hamiltonian matrix, like I said, this is what it looks like. And these are the momenta that you would be used to. We saw those in one of those earlier ones in these pictures in these units, 1 to 2 inverse Fermi here. What this says is that these low momentum things, those little soft guys in the nucleus, are going to have a high probability, this is very, very high here, to turn into a high momentum. Okay? And that creates the short range correlation. So this picture tells you you're going to have that high momentum picture. And that makes almost every method that you want to use to solve the nuclear many-body problem fail until you apply something like this. So what does it look like? Let's actually see it in action. This is that Hamiltonian matrix with the scale ramped down to make it more visible what happens. So just to mention here, green is going to be 0. Here's a 3D version of this same matrix. What we're doing is driving this toward the diagonal step by step. And I'll show you some intermediate steps. So here's the first intermediate step, another one, you can see it's getting lighter. These things are getting weaker on the side. It keeps going. And now we have basically this picture. We've basically been doing matrix transformations by a differential equation for every matrix element in here. And we see down low, low talks to low, and high talks to high. What does this look like for the interaction now between these 2 low momentum nucleons? Well, this is tricky to change this back to a potential, but you can do it for the low momentum nucleon. Kyle Wendt, who was a grad student here, figured out how to do this. This was the original one in blue. Now I'm taking some steps. These are snapshots. And you note this hard core, that repulsive core just melts away. And the final answer is just a nice, simple potential like you might see in your undergraduate quantum case. This is both soft, doesn't have the hard part, and universal. This was another potential that we started with here. when we run this transformations, we get the same answer, something that looked completely different. So this was another feature. That was the thing that Wilson introduced in this. So what, oh, that's right. There was the other part of this potential, which was this tensor, which is even worse. It's off the scale here. And they just go to some nice little soft thing. So this was all good. And we went basically from a potential that looked like the red to one that looked like the blue. And what did it do to a wave function? This is the Deuteron wave function, the only bound state of two particles. It originally looked like this black one here, where it dives down because it costs a lot of energy to be close to each other. This is the relative distance between the neutron and the proton. This is the Schrodinger wave function. This part here is from the tensor force. It mixes the L equals 0 and L equals 2 state. That's not something you talk about in quantum mechanics. You say they don't mix because you have central forces. When we evolve this to the place we're going to do the calculations, all of these different wave functions become the same wave functions, and they're all nice and simple. None of this one where you care about whether they're close to each other. And the amazing thing about this is that none of the energies or those phase shifts or the binding energy changes. This was done by a current graduate student, these pictures here in connection with some of his calculations. And so, so let's put this together then. We now have that we have the wave functions are much simpler. How is it that we got this idea that we still can explain these experiments? Well, to do that, we have to remember what happens if you get rid of short wavelengths. So we've decoupled them this way. We've made the short only talk to short and high talk to high. If I have short wavelengths, then if I imagine this as two beams of light through your eye, looking at two stars, and this is your retina, you can see that you can tell them apart. They're spread out because of diffraction. But if we go to red light instead of blue, they smear out. And what was 2 becomes 1. So if I imagine this as my photon beam in the experiment, instead of seeing 1 nucleon, you see 2 nucleons. And that is what happens with this here. These were the 2 ways of viewing this picture, my Roshuman explanation. And we can see that working in our pictures here. This was the potential that went to this diagonal form. This is a different potential than I used before, which is why it looks slightly different. But again, low talks to low and doesn't talk to high. If I look at this operator here, this one here, here it is originally. This is the one that only talks to a high momentum nucleon. As we evolve it, this part develops here. And this is this 2-body part. If I now take the wave function that comes from here, which only has low momentum, and sandwich this operator in between, all that high momentum stuff goes away. So this part goes away, and you're left with a pure 2-body. And if you go ahead and then do this, I have, it's a long story at this point, but we're stopping here. All of the features that they found in those experiments with knocking these things out are exactly reproduced. And they're exactly reproduced because this is a unitary transformation, and unitary transformation preserves eigenvalues and everything else that you can actually measure. Okay. So if we revisit this nuclear Roshuman effect, we're going to change it to the RG Roshuman effect, which says instead of contradictory, but alternative interpretations are possible. Can we explain all the phenomenology? The answer is yes. Is one resolution better? this is a controversial question, The experimentalists or the theorists who work with the experimentalists on this don't like this very much. But I would argue that the lower resolution that we use for nuclei are actually much better to use. Okay, again, that's a kind of long story. So going forward, what are we doing with this? These are incredibly cool experiments because they can isolate this kind of physics that involves knocking out the two nucleons, okay, which enables us to calibrate our reactions and our description of the reactions. This is really important because the facility for rare isotope beams is about to start up next year, hopefully next year, at Michigan State. And the reactions there are much more complicated. Instead of having this one body become to a two body interaction, they're both mixed up. And so we really need to understand this. And this is what we think using this type of analysis, we'll be able to understand it and then explain the data that they're going to find. And that's my story. So thank you very much for listening. Now we can have the pizza.
Thank you very much. We've got about 5-10 minutes left. Does anyone want to ask any questions? Yeah, I know renormalization's group is a little scary. It's the
it's actually just really cool. It is scary, some of the concepts there, but it really is what I was showing you there was just linear algebra, you know, that we were doing. We were doing matrix transformations of our Hamiltonian bit by bit to make it work. So. But it's really this concept that you can take a picture and completely change it without changing the experimental results is just very cool. There's a pizza slice, very good. Those are pepperoni, I assume, the canonical pizza.
Yeah. This is probably the most explicit explanation I've ever had of renormalization group. I've heard Dr. Perry speak on it 3 times.
Oh yeah.
Which you'd think I'd be tired of it, but every time I understand what's going on a little bit more.
Yeah. I find you know, you can look at it different ways. I really find thinking about it in terms of matrices and thinking about what a Hamiltonian matrix does. I mean, you spend most of your time in, usually in, or a lot of the time in quantum mechanics class, thinking of the Schrodinger equation, you know, thinking of wave functions and stuff. But it's actually much clearer to think about the matrix form, you know, sort of Heisenberg instead of Schrodinger way of looking at things. And then it becomes much clearer what is happening that you know, it's unbelievable looking at this. If you think about this, you know, with the numbers, this has exactly the same eigenvalues as this one. So all the energies predicted by this up to its highest energy are exactly the same as that one. And it's just linear algebra to go from one to the other. But that linear algebra then turns into physics, which is critical.
So you said earlier on in the presentation, you said at one point it looked like the other group of people was coming out on top, but you were still kicking around working on this sort of ideology. Yep. Are there still people from the other side kicking around?
There are all of the people doing associated with the experiments are still in this camp. Okay, so part of the reason I was giving a talk on this last week was I was invited by people who wanted to have an opposing view, talk to you know, an audience which included all of these experimentalists. And I gave a talk. I was invited for the same reason to talk in Germany in December,
Schön.
virtually in there, because all the experimentalists have this picture in mind, have that picture with all the short-range correlation pairs. And they're just, and there's associated theorists, and they just keep saying, oh, this one's not going to work. and we just, you know, keep showing that it works. So we're writing up a paper now that has a lot of these. I made this talk in part to make it accessible for the experimentalists, because, and the theorists doing it, because giving the more technical one never was convincing. You know, if people have a picture in their mind, you have to give them another picture, or they're not gonna believe it, right? Physicists, it's really important for us to have intuition, and there are a lot of very good physicists who have this intuition and can figure out things with them. The fact that there could be another intuition is just a really foreign idea. Okay.
Yeah, well, if no one else has any questions, then thank you very much, Dr. Furnstahl.
And you're very welcome. And I hope everybody has a, if you're like the people in my class, you have a lot of midterms coming up. So I wish you luck on that.
Thank you very much.
Okay. So, night, everybody.